Hey, thanks for watching this video. In this video, we're going to do a full tour of all of the components within a heat pump system. Now, we're not going to get into the diagnostics or really deep into any one in this video. Those are going to be in separate videos. But this video is designed for somebody who's very new to heat pumps or very new to air conditioning or refrigeration in the first place. And this is going to help give them a really quick onboarding to everything that's involved in a heat pump or even a typical air conditioning system. So to start with, let's talk about some of the basic components. You first have the compressor. The compressor is called the heart of the air conditioning or refrigeration cycle or circuit. It creates the pressure differential. Here at HVAC school, we call the compressor the pressure increaser. Out of the compressor, you have the discharge line that is full of high temperature, high pressure vapor or gas. It goes into the condenser. The condenser then rejects heat. We call the condenser the heat rejector. And it turns that high pressure, high temperature vapor into a high pressure, medium temperature, little over outdoor temperature liquid. Goes out of the condenser into the liquid line, down the liquid line, back inside on a split system, because that's what we're showing here, to the metering device, which is usually a TXV or a piston type, piston being a brass fixed orifice, TXV being an adjustable type. I like to call the metering device the pressure dropper or the pressure decreaser. So once the refrigerant leaves the metering device, it begins to boil as that pressure is dropped. In the evaporator coil, boiling refrigerant actually happens at a low temperature, and that absorbs heat. That's the evaporator's job, is to absorb heat from the space. So on a split system, that evaporator coil in cooling mode is on the inside, and it's actually picking up heat from inside the occupied zone. Once the refrigerant is completely boiled off, so it's completely changed from liquid to vapor, that refrigerant travels back down the suction line, back to the compressor. Now on a heat pump, there are a couple other specific items that make a heat pump a heat pump. One being the reversing valve, often called the four-way valve, that shifts so that way either the condenser is outside or inside. The evaporator coil is either outside or inside. In cooling mode, the evaporator coil being inside and the condenser being outside. In heating mode, the condenser coil being inside and the evaporator coil being outside. That reversing valve interrupts the lines coming out of the compressor to make that shift. You also have a component called the accumulator. The accumulator's job is to protect the compressor from liquid refrigerant that may be coming down the suction line. All that liquid refrigerant should be boiled off in the evaporator coil, but there's certain circumstances where it may not be, and the accumulator prevents liquid refrigerant from making it to the compressor. The liquid line filter dryer goes in the liquid line, and its job is to catch any particulates that may be left in the lines or in the system or may be generated within the compressor over time with wear, and it's also there to help dry out any moisture that was left in the system. Now, you shouldn't have any significant moisture in the system because you evacuate, you pull a vacuum on the system, and that should remove that moisture, but the liquid line filter dryer is there just as a backup plan. On the outside, we also have a suction line service valve and a liquid line service valve that is built into the condensing unit. Those are the valves that you actually open when you initially put the outdoor unit into service, and they can also be used to isolate the outdoor unit. There are ports on the side of those valves that have a Schrader Core in there, which is similar to the valve on a car tire, so that when it's pushed in, it allows refrigerant to enter or leave that valve, and that's how we connect our service hoses to the system in order to access it, or our test probes. There's also something called a suction line filter dryer, which is not shown here. These are generally not installed in residential applications off the bat, but they can be installed after the fact if there is a service repair, such as a compressor replacement. So that's the brief overview. Now let's go ahead and look more at the 3D model and go through some more of the specifics. Thanks for watching. This video is about a split system heat pump, which is something that we see a lot here in Central Florida where I'm located. This layout is going to be sort of a typical layout that we see throughout our market. There is going to be some slight variations from system to system. But first, let's take a look at the inside unit. This is what we call an air handler or a fan coil. The outside unit is what we would call the condenser or condensing unit. And it's also often what people will call the heat pump portion. But really, what makes it a heat pump is just whether or not it has the controls that allows it to shift from heating to cooling to bring heat in from the outside and pump it inside. It really has a lot of the same components that an air conditioner has. First thing you need to find whenever you're going to work on an air conditioner are the proper disconnects. Those are going to be your on-off switches or circuit breakers that shut the equipment off, and then you want to test with an electrical meter and make sure that power is off before you're going to work on these systems or remove the panels. There's usually going to be an outdoor disconnect that looks like this one here, And then if you go to the inside, often there'll be a circuit breaker like this, even integrated inside the air handler, or maybe it could even be a wall switch or some other type of disconnect method. The first thing I want to talk about is the compressor. In this model, we're talking about a scroll compressor. A scroll compressor uses a fixed scroll and an orbiting scroll. The fixed scroll is on top, and the orbiting scroll is driven by a motor, which then creates increasingly smaller pockets that trap the refrigerant and pressurize it and create the pressure differential to get the refrigerant moving through the system. The refrigerant is the medium that we use to move heat around by compressing it and then expanding it once again, as well as a phase change. So if you take a look at this compressor, you can see that the refrigerant goes into the compressor shell as a cool vapor, and then it is drawn into the compression chamber, and it gets continuously higher pressure and higher temperature until it is discharged into the discharge line as a high pressure, high temperature vapor. While we're out here talking about the compressor, let's also take a look at the accumulator. The accumulator's job is to catch any liquid refrigerant that may be coming down that suction line. Now, the evaporator coil is supposed to boil off all the liquid refrigerant and turn it into a vapor before it gets to the compressor, but there are some extenuating circumstances that can become impossible, especially in a heat pump where your evaporator coil is now outside and it's more difficult for the system to control for that, especially when it has a check flow piston metering device like we show on this system. So you'll find accumulators on a lot of heat pumps and some other systems as well. And as you can see, the way it works is the vapor refrigerant drops down into the bottom of the accumulator along with the oil. There's a little pickup port at the bottom that allows the oil to be drawn back to the compressor, as well as a little bit of liquid refrigerant, but it controls it enough so that it's not going to damage the compressor. So you could have a good amount of liquid inside that accumulator and still prevent slugging or flooding of the compressor, which is when we get a lot of liquid refrigerant back to the compressor, which is an undesired situation. But we still have that little pickup port, which allows us to bring oil back to the compressor. Next, it exits the compressor, and next it goes into the condenser coil. This is an air condenser coil, which means that it rejects its heat to the air, at least in the cooling mode, which is what we're showing right now. And the air travels over those fins. The outdoor air is going to be a lower temperature than the temperature of the refrigerant in the condenser coil, and that's what rejects the heat out of the refrigerant, and therefore also out of the house. In terms of the refrigerant in the condenser, the refrigerant comes out of the compressor as a high temperature, high pressure vapor. It goes through what we call the de-superheating phase, where it drops in temperature from a higher temperature until it reaches what we call the saturated or condensing temperature. This is the temperature at which it begins to change state to a liquid. Now, it starts off at 100% vapor and then makes its way to 100% liquid, and everything that is in between, that entire middle part of that condenser coil, is going to all be the same temperature. It's just rejecting its heat to the outdoor air, and that heat is changing the refrigerant from a vapor to a liquid, no longer changing its temperature. Similar to what happens in a boiling pot of water. When you're boiling it, water boils at 212 consistently at atmospheric pressure until it is completely vapor, and then it could be superheated. In this case, it's starting as superheated vapor and it's working its way down to complete liquid. Once it gets down to the bottom of the condenser coil, then it can be completely liquid and it can drop its temperature below the saturated temperature and begin to subcool. Once we leave our condenser coil, it's completely liquid. It travels down our liquid line toward our inside unit and reaches our indoor TXV. In this case, we're showing a TXV, but it could also be a fixed orifice, which we'll show on the other side of this heat pump circuit in a second. TXV is a very common type of metering device. It provides the pressure drop. We often call it the pressure dropper or the pressure decreaser. So it takes that high pressure, warm liquid refrigerant, it drops its pressure, which then allows the temperature to be significantly lower in the evaporator coil. There are several forces that affect the TXV. You have the bulb force and the external equalizer force, as well as the spring force. By adjusting the spring force, you can set the outlet superheat, which basically just means you can decide how far you want the liquid refrigerant to boil in that evaporator coil. Now, when we say boil, many people think boil as being hot. In the case of an air conditioning system, refrigerant boils cold. It boils at a low temperature inside that evaporator coil, and that's how we get heat out of the home. The evaporator coil is what we call the heat absorber. It picks up heat from inside the space as the air flows over the evaporator coil, and it drops drops the temperature of the air before it blows it back into the space. So it acts as almost a heat sink, or it grabs the heat into that boiling refrigerant as it is low temperature, low pressure, expanding through that evaporator coil. The refrigerant enters the bottom of the evaporator coil and travels up and then leaves through the suction line. As it goes down through the suction line and back outside again, now it is a low temperature, low pressure vapor once again, headed back to the compressor. I want to pause for just a second and show you the service valve, and in this case, a heat mode metering device on this heat pump system. On a heat pump system, this system has the ability to switch modes between heating and cooling by redirecting the flows through the reversing valve. And so in that case, you are going to have a separate metering device outside. In this case, I'm showing it as a piston. It won't always be a piston, but this is called a check flow piston, so that when the refrigerant is flowing in the cooling direction, it will be unrestricted. It will unseat that piston and be unrestricted. But then when the flows go the opposite direction, it seats the piston, and that forces refrigerant through it, which then makes the outside coil the evaporator coil rather than the condenser coil. So that acts as an outdoor metering device. Also here you can see, just going to show you quickly the operation of the service valve, how when it is front seated or tightened all the way down, then that shuts off flow. And when it is back seated or turned completely counterclockwise, then that allows full flow through the valve. Back out at the condensing unit, I also want to show you the condensing fan motor. All fan motors are basically just rotating electromagnets that spin based on the change in frequency of the power coming in from the power company. So in the US, our power shifts every 60 times every second, what we call 60 hertz. And so that frequency is utilized in that switching of the electromagnets in order to spin that fan motor. It's important that the blade is positioned properly in the shroud in order to pull air over that condenser coil and blow it out in order to discharge that heat away from the coil. Another thing that makes a heat pump is that heat pumps will have a defrost board. And the defrost board just works to help deal with frost in the outdoor coil when the system is running in the heat mode. Because when the system is in heat mode, the outdoor coil becomes an evaporator coil and the indoor coil becomes the condensing coil. So you have to have a defrost control in order to deal with frost that's going to naturally build up on that outside condenser coil. They usually use sensors mounted on the coil as well as an air sensor. It's the most common strategy here. We're showing an Emerson board, which is an aftermarket, very common board used to deal with defrost. Now let's go back inside, and I want to show you the liquid line filter dryer. Often these will be installed outside, but generally speaking, they should be installed inside where they're protected from the weather. The liquid line filter dryer, in this case, it is a biflow dryer. It will either have bead desiccant inside or a solid core. Either way, it has some method of cleaning up the refrigerant for particulates, as well as helping to pull the moisture out. And that's what the desiccant's for. The desiccant grabs that moisture. But you can see with this check design, it can work in both directions. So if the flow is going in heat mode direction, it will work, and as well as if it goes the other direction via check valves on both sides of that biflow dryer, where a single flow dryer or a one-directional dryer only works in one direction. Now we're going to take a look at the blower motor and the blower wheel. There are several different types of blower motors that are common, but most designs are going to look very similar to this. The blower wheel, often called the squirrel cage, uses the cups in order to basically scoop the air and blow it out through the ducts. These types of designs allow you to push air against significant back pressure, whereas the outside condenser fan is efficient for moving a lot of air. It's not as efficient at working against back pressure. A blower wheel design is good for working against the pressure of ductwork. Because this is a heat pump, I also want to introduce you to the heat strips or the auxiliary heat. Heat strips are just there to provide some additional heat in cases where the heat pump isn't keeping up with the load or when the heat pump is in defrost. When the system goes into defrost, the defrost board energizes the heat strips on the inside, as well as shuts off the condenser fan on the outside and shifts the unit back into cool mode to defrost any ice that may have built up on that outside coil. That's one case where the heat strips will run, and another is when it's just cold enough outside that the heat pump alone is not keeping up, and that forces the heat strips on. Let's take a look at the transformer. The transformer is another part that you're going to want to know. The transformer takes the high voltage power on a fan coil that's generally going to be 240 volts. On a gas furnace, that would generally be 120 volts, and it's going to convert convert it down to a safe 24 volts that we can then use to energize the low voltage circuitry on the system. That's going to go to your thermostat, and then from your thermostat's then going to control the different portions of the system, with the common color codes being G for blower operation or fan operation, that would be G or green, R being red or hot, which is constant 24 volts, C would generally be common, which is often used with blue, sometimes black, which is the path back to the other side of the transformer. You have W or white, which is used for heating, and in the case of the heat pump, it's used for auxiliary heating or electric heat on the inside. You have yellow, which is used to energize your compressor contactor in a heat pump. On a straight cool unit, you would just call it cooling, but it's what turns on the outside unit. And then you'll often have orange, and then maybe even some auxiliary terminals. And then you'll often have an O terminal would be most common, which is what energizes the reversing valve in cooling mode to keep the system in cooling on a heat pump. You may also have other terminals for dehumidification, and often those will be accessory terminals that connect into the D or DH terminal inside on the blower board. Now let's take a quick look at the blower board and its wiring connections. On a fan coil, they're often going to look something like this. On a furnace, it will often be a larger board called an integrated circuit board. But on this board here, you can see that your wires going to your condensing unit or your outside unit, as well as your thermostat, all connect in. And you'll also see that we have the wire nut here that connects in our float switch, which shuts the unit off should you have a drain backup. If you take a look down at the float switch, you'll see it's connected into one of the ports on the drain pan. So in case the water level in the drain pan gets up too high, it will shut the system off. Let's take a quick look at the condensate drain. The condensate drain has to be trapped and vented and pitched outside. In some cases, you won't have a vent like this. In Florida, it's very common that these drains will just run underground and then outside. It's not ideal, but it is the way that often they are set up. But it will still drain out outside, even if it goes down and back up, because of the weight of the water or the column of the water that's pushing it out. But at the end of the day, whether it's a heat pump or a straight cool system, the goal of the system is to either take heat outside and put it inside, or inside and put it outside. If you're running in cooling, you're taking out heat from the inside of the house, you're absorbing it into the evaporator coil, which is then bringing it out through the suction line and back to the compressor, where it's then rejected outside. If you're running in heat mode, then it's just a shift of the reversing valve, which then makes the inside coil the condenser, the outside coil the evaporator, which then allows heat to be put inside the home. And that's why we call it a heat pump, because it's pumping heat into the inside from the outside. All right, now that we're complete with the 3D model, I just want to make sure that we don't miss some of these components in the electrical side. So let's talk about some of our low voltage electrical components that we already covered, but just hit them again real quick. Your transformer's job is to change it from 208 or 240 volts down to a safe 24 volts, which can then be used to control the equipment, your thermostat, your boards, those sorts of things. You also have a 3 amp or 5 amp control fuse that protects the low voltage circuitry to make sure it's not going to be damaged in case you have a short or some other low voltage problem. If that fuse blows, there's a reason why it blew, and you need to find why that happens. Most commonly, it's because of a low voltage short circuit. You have thermostat wires, often called control wires, where you have multiple conductors in a single cable between your thermostat and your air handler, as well as in between your air handler and your condenser, and that allows the equipment to be controlled by the thermostat. You'll often have safeties. These safeties will be a condensate overflow switch, often called a float switch, that protects in case you have a drainage overflow. And then often on the outside, you'll have low pressure, high pressure, or loss of charge switches, which trip and shut off the system in the case of low or high pressure on the refrigerant circuit. Like we mentioned, you have your thermostat, which acts as your main system control for comfort, so it turns the equipment on and off and in the proper modes. You have your blower board, which controls your blower. Sometimes in variable speed applications, it will also control the speed of your blower at different stages and under different circumstances. And the outside, you have your defrost board, which is in charge of controlling that outdoor unit, especially during defrost. So when there is ice on that outdoor coil, to get that off during heating mode. You have your compressor contactor, which acts as the main switch that shuts your compressor and your condensing fan, your outdoor fan, on and off. And then you will often have a sequencer or heat relay that controls your auxiliary heat strips, those indoor heat strips that you need in cases of defrost or in cases when it's very cold outside. And then finally, we have our high voltage components. We have our condenser fan, which is our outdoor fan. We have our blower motor, which is our indoor fan that blows air inside the space. You have your heat strips, which are those high voltage electric heaters that are used generally for backup heat. Sometimes they're primary heat in markets that don't get very cold at all, like South Florida. And then you have your compressor, which is the heart of the system. It can be either a reciprocating or a scroll compressor, or maybe even a rotary compressor in residential applications. And those are all just different technologies that do the same thing, create compression and a pressure differential and move refrigerant through the circuit. One other thing you'll see in some cases is a crankcase heater, and the crankcase heater is there so that when the system is off, when that compressor is not running, it keeps the compressor warm and prevents liquid refrigerant from condensing inside that compressor, which can cause what's called a flooded start and cause damage to the compressor. Now, I know that was a really fast overview. Some of you are going to be completely overwhelmed by that, but you can slow it down and you can go back through it. For those of you who are very new to the equipment, maybe you're starting in school or you're starting as an apprentice, this can help you get your head around some of those most common components, especially if you work in a heat pump market. Watch out for future videos. We're going to go over more diagnostics, service procedures, those sorts of things on this same 3D model. But for now, hopefully you found that helpful. Thanks for watching. We'll catch you on the next video. Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.